Good morning, ladies and gentlemen. This is a panel which is near and dear to my heart. It's about data, algorithms, and infrastructure. And as you have seen from yesterday's presentations, there are many of us that now take on very large-scale data sets, and those might be publication, patent, funding, news data sets. And some of these data sets are slow in their dynamics. Books, for instance, grow very, very slowly. However, there are other data sets, such as social media data sets, which come in big data pipes. And the big question is, how would we actually leapfrog some of our academic and maybe also government infrastructures to match what is already common in industry? And it's a true pleasure to introduce the panel to you and ultimately also to moderate the panel. Given that we have 5 speakers, I will be very brief. I would like to help you understand that we have 2 representatives from the National Institutes of Health. We have James Onken and Jan Hutchins from the NIH Office of Portfolio Analysis. Jan was added yesterday to the panel, so you might not see him in your printed handout, but he's online, so you can find all bios of all 5 speakers online. We also have Richard Freeman from NBER at Harvard University, Nachum Shaham from PayPal, and I think it is very important for all of us to understand exactly what infrastructures actually industry is using to deal with extremely large data sets, which also need to be secure and which have a huge impact on how we do our business today, but also how we live our personal lives today. And then last but not least, Grace Peng, also from the National Institutes of Health. She is working on very, very interesting efforts to actually standardize the description and the retrieval of different models in the biomedical domain. But again, I believe here we in the science of technology and innovation research can learn and potentially also leapfrog to some of the standards that are now emerging in the biomedical domain, as we also should be aiming for high reproducibility of results and for new ways of sharing not only data sets, but also tools, and ultimately also finding ways to develop infrastructures that ideally all 3 of us, industry, academia, and government, can use collectively to share data and to run the algorithms we really need to get a better, more real-time insight into how science, technology, and innovation really grow and work over time, and how we can proactively steer it, having that situational awareness that was mentioned yesterday. So without further ado, I would like to ask Jim Onken to present. And after him, it will be Jen Hutchins, and then Richard Freeman, then Nachum Shaham, and Grace Peng.
Thank you. Well, good morning, all you morning people. I'm not one of you, but I'll do my best. And I've, as usual, over-prepared, so consider this an 8-minute flash presentation, flash talk. So I work in the Office of Extramural Research at NIH, and as over the, I'd say the past 5-10 years, interest has grown in metrics, quantitative analysis, modeling, simulation, and so forth. We have found that a major impediment to us is having ready access to high-quality data. And so I'm not going to talk about any of those modeling and simulation efforts. What I'm going to talk about is what we're doing to solve that problem for ourselves so that we can provide, so that we can streamline things and provide people with the information that they need who are interested in doing these kinds of analyses. So this is not a new problem. This is the National Academy of Sciences often does analyses of NIH programs, and in almost every report they do, you will see a reference to the fact that the committee was not able to get information that they needed for their study. And so this is one from July 2003, but I could have picked almost any report. And as they noted here, that we need to make, NIH needs to make improvements in its data infrastructure. More recently, NIH itself has had a couple of committees who have said the same thing. This is the NIH Advisory Committee to the Director in 2012. In 2014, the NIH Scientific Management Review Board did a study on how to assess the value of biomedical research. And again, National Academy of Sciences, 11 years later, says the same thing that they've been saying all along, which is we need better data. And these last three reports have also emphasized that we need linked data. We need to take our data from our administrative databases and link it to other existing data sources. So here's an example of the kinds of things that are done with linked data. This is a report last year from Battelle, who took our administrative data from the Reporter database, that's the online database of NIH-funded research, and they linked it with Thomson Reuters innovation data from by mining the government intersection of the USPTO records. And they looked, I don't expect you to read this, but they looked at the number of patents that were linked to different grants from various institutes at the National Institutes of Health. And their finding is that the largest institute, NCI, has the most linkages, but interestingly, the second greatest number of linkages was with the National Institute of General Medical Sciences, which is the basic science institute at NIH. I thought this was interesting because 20 years ago, we said the same thing. This is the appropriations testimony from NIGMS, who said that NIGMS is the second among all the institutes in the number of grants that they're able to link to patents. And I remember this because I was the project officer on the contract to do this study, and we paid Francis Nairn money to link these data together. And then we did reports like this for our testimony for to appropriations. We did some reports to our council. And then after a couple of years, the data got stale. I don't know what happened to the data. We probably lost it when I got a new computer. And the point is, between this 20 years ago and the Battelle report, NIH grants have been linked to patents over and over and over and over again by many different groups of people. And then when their grant or contract runs out, the data gets stale, and we have to do this over and over and over again. So the idea behind our effort, which we call Portfolio Analysis, Reporting, and Data Infrastructure, or PARTI, is to develop these linked data sets, but maintain them on an ongoing basis, so that every time someone wants to do a study, they don't have to recreate the wheel, link all these databases together again. And we're looking at different ways of linking databases. We have, right now in Reporter, we have publications linked to grants based on a direct citation. That is, the authors have acknowledged the NIH grant in the acknowledgements section of the papers, or they've reported it on their progress reports, and we do a direct match of the grant numbers to our administrative data. But there's other ways, and we do that for example, for press releases as well. These news services that our grantee institutions use can tag their press releases with grant numbers. We ingest that information and make it available in Reporter. But there's other ways we could do this linking. You know, we could use things like named entity recognition to mine press releases for investigator names, institution names. We could characterize the nature of the science being described in the press release and link it to our grants data that way to create some probabilistic matches between these various documents that are produced in our NIH funding. This is our system architecture, which I only present just to show you what we've been able to load this far. So we are taking clinical guidelines. These are practice guidelines that are issued by authoritative bodies. They contain references to the underlying science. We mine the references from those clinical guidelines and link it to NIH funding through the papers that are referenced in the guidelines. So we've got about 1,000 guidelines where we've mined about 100,000 references from them and linked them to NIH grants. We've done the same with clinicaltrials.gov, which includes not only references to grants that were supporting the clinical trials, but clinicaltrials.gov also contains publications resulting from the clinical trials. Again, we're able to link those through the publications, acknowledgements to NIH funding. We've loaded Thomson Reuters Web of Science database, and Ian's going to be talking about another database that their office is working on called iSight, which also contains publication information. We have loaded information from the FDA Orange Book, which is the FDA's database of approved drugs, and the patent information related to that. FDA Purple Book is the same thing for biologics. And we've loaded the USPTO, and Ian's office also is working on something called iTech, which is related. So what we want to do with this kind of information is to be able to support both qualitative and quantitative kinds of studies. So this is an example of what's sometimes called a tracing study, a qualitative description of NIH's role in some scientific advance or some product. This one is the development of Gardasil, a vaccine for human papillomavirus. And this was done by our Division of Planning and Evaluation. The analyst, Preeti Joshi here, who did this study, estimates that she spent 200 hours gathering these data from various databases, linking it together, and trying to lay out on a timeline the significant advances supported by NIH in the development of the HPV vaccine. What we want to do is to facilitate this kind of research by doing the linking for people. So this is a proof of concept system that we call Retrace, which takes the party database, and we can search the database for a term such as papilloma. It will retrieve all of the documents that refer to papilloma, either in the title, abstract, what have you. The different little indicators of what type of document is returned by the system. We have NIH research projects, press releases, patents, clinical trials, publications, and so forth. And then the ones that we're able to link to NIH funding are also indicated to the user. And they can use this information also to see networks. So this is the HPV vaccine here in the middle of this network, all of the related patents and publications linked to it. And they can drill down into this network, view the underlying documents through linkages to the USPTO database or PubMed or PubMed Central. And then if they decide that these are documents are significant in the history, they can drag them and drop them to a timeline over here on the left and create a historical timeline, the development of the HPV vaccine. We can also do quantitative analyses of these kinds of networks. So this is an example that was published last year in Cell by Sandy Williams and collaborators at the Gladstone Institute and UCSF, where they've essentially done a similar kind of thing. This is, and they label this Cure Network Informatics, this approach. What they've done here is they've taken a patent for ivacaftor, which is a drug for cystic fibrosis. They've linked to this patent all the clinical trials that supported development of the drug. They've linked the trials to publications indicated in green, authors indicated in purple, and institutions indicated in blue. And then the yellow nodes here are those that they've done graph analysis to identify what are the critical nodes in this network and what are the most important authors, institutions, publications in the development of ivacaftor. And if you read their paper, they'll give you the list of the 10 people and institutions involved, and it has the face validity that you would expect. So we've done the similar kind of things with our party database. This is the network for Repatha, which is a drug released last year for lowering of LDL cholesterol. We're able to link the Repatha patent to clinical trials, other patents, and literature. But we've also then been able to link that literature to the NIH funding, acknowledged in that in those papers and the grantee institutions. And the yellow dots in our network here are those publications that received NIH support. And now, since we've generated this slide just in the past couple of weeks, we've been able to do the similar kind of analysis on this network to identify what are the critical nodes in this network, who are the important NIH grantees, and the results were pretty satisfying. We were able to identify the Nobel Prize winners who identified the LDL receptors and so forth. So, and we've shown this to some experts in the area, and again, we're able to have some face validity to the results of this kind of analysis. So we've made presentations on this in the past, and everyone says, well, why are you going to make these data public? And yes, to the extent that we can, we'll be making the data public the same way that we currently do in Exporter, which is NIH's database of NIH-funded projects, the publications and patents linked to those, and clinical trials, and all of the link tables allowing you to link all those tables together. We're doing a similar kind of thing now federal-wide with something called Federal Reporter. This is part of the STAR Metrics initiative, where we've combined the research funding from these different federal agencies, and we're starting to, you can get abstracts to the projects, and also we're starting to link the funded research to the publications. So we've got publications from NIH and NSF loaded in the database, and we'll be adding over the next year publications from other federal agencies. Like the NIH version of Reporter, we have a federal exporter. So far you can get the project and abstracts. We'll be adding publications to the federal exporter as well later this year. And then finally we have World Report, which is a system being supported by NIH, the MRC, Medical Research Council in the UK, Bill and Melinda Gates Foundation, European Union, and the Canadian Institutes of Health Research, who are all supporting an effort this year to take what has been a proof of concept for the past couple of years at this URL and to redesign the site, put a new skin on it, and expand it from a proof of concept which was just focused on sub-Saharan Africa and make this a worldwide database of research funded by various funders around the world. And these are the list of funders, including Wellcome Trust, INSERM, Institut Pasteur, Max Planck, Swedes, and so forth. So you'll be able to go to a World Report and again be able to export all the data of the research funded by these different organizations worldwide. Just acknowledgements to our collaborators, other offices in the NIH OD that we're working with. We have a party working group with about 25 or 30 people from across the NIH helping guide this effort. Our contractor, NETI Solutions, does all of our development work, and Brian Zuckerman and Will Doan and Sharon Williams from Science and Technology Policy Institute are doing high-level requirements gathering and helping us plan this effort. And these are the staff in my office, and I guess we'll probably take questions later. Right? Okay. Thank you.
Are there any quick clarification questions for Jim? How many of you were familiar with the World Reporter? Okay, 6. Very good.
All right, well, thank you, Katy, for having me here to talk about our work to explore and measure scientific influence. And thank you for that great lead-in, Jen. I appreciate it. So our work in this issue really began at about the same time that the scientific community itself was coalescing and coming together to decry current research assessment practices in general, and in particular the inappropriate use of impact factors in career progression decisions. So this is something that got a lot of attention from a variety of journals, editors, and scientists, and it really laid the groundwork for how we can move forward to improve research assessment in the scientific community. So the major conclusions here were that there's no substitute for a careful evaluation of the scientific content that's being produced by researchers, and that there needs to be supplementation by a variety of article-level metrics that can each reveal different facets of the work in question. And so this is where we were coming in, looking to help generate metrics like that. And one of the problems at the time was that the currently available metrics weren't very well suited toward that task. So blunt metrics like publication counts and impact factors are limited by field dependency, being journal level rather than article or individual level. Tools like article citation rates were a little bit better, but still suffer from field dependence. And tools like H-index are very time dependent. So older investigators tend to have higher H-indices than younger investigators, even if they're producing very similar quality of work. So this is where we came in. We wanted to develop something that met the need of funding agencies and the scientific community at the same time. And there were some considerations that we had to make. So one assumption that we made that's very common in developing citation matrices is that the citation of a publication reveals value to or influence on the citer. We know that's not universally true. There are things like negative citations, but those tend to be comparatively much rarer. And it's generally accepted that citation rates are an indication of the breadth and speed of diffusion of knowledge amongst the scientific community. So we saw a need for an article-level metric that is independent of field, journal, and time. And what we set out to do was answer a simple question. How many citations per year is this article receiving compared to peer articles in the same field? There have been a number of attempts over the years to develop metrics to address similar questions, and the devil's in the details. So what we've done is actually a very old idea, just comparing the citation rate of an article with the expected citation rate based on peer performance. Now, what does that mean exactly? What we've done is we've benchmarked the citation rate of a journal, or of an article, to other articles that are in the same peer group, in this case NIH-funded articles, in fields with the same intrinsic citation rate. Now, how do we determine that? There are a few approaches for determining field citation rates. Some people use journals as a proxy for field. Some people use categories of journals, like biochemistry journals, as a proxy for a field. What we've settled on is the use of co-citation networks. This uses information that's inherent in the citation network. And the idea might sound complicated, but it's actually fairly simple. So if your article is the one in red, and you're interested in developing a metric like this, the co-citation network is simply the reference lists of the 3 articles that cite you. So up on top here, we've got 3 articles citing your paper, and the combined reference lists of those 3 papers are the co-citation network. So in this way, we've developed a metric where an RCR of 0 corresponds to a paper that's never been cited. An RCR of 1 is accruing citations at the average rate for an NIH-funded paper in the field. An RCR of 2 is accruing citations at twice the rate of the average NIH-funded paper in its field. And an RCR of 20 is exceptionally highly cited. So why is this so important? Well, I'm gonna give you an example on this graph here. So I've plotted the RCRs of articles that were NIH-funded from 2003 to 2010, and slice them by journal. So you can see here box and whisker graphs showing the distribution. And on the left, we have journals where scientists get an exceptional amount of credit for publishing in. But you can see that in each of the journals to the right, which are progressively lower impact factor, there are articles in each of these journals that have an RCR that's higher, as high or higher than the median of the RCRs of papers in Nature, Science, and Cell. Now, this might seem like a trivial point, but we found that actually the vast majority of highly influential articles are published in journals that are not high impact factor journals. So what we are hoping to see is the use of metrics like this to supplement expert opinion in order to give more credit where credit's due, so that scientists who are publishing highly influential work in less visible venues are able to get the appropriate amount of credit for that. To that end, we've deployed a web tool called iCite, where you can go and plug in the PubMed IDs of any paper that's published in PubMed and get the relative citation ratios, as well as a panel of other bibliometric indices. The link is down here on bottom. And I think I'll stop there. I might have to leave a little bit before the official end of the panel here. So if you have questions and there's not time to address them beforehand, you can send those to the director of our office, George Santangelo, or myself. Contact information's here, and if you want more details, there's a preprint manuscript on BioArchive at this lab. Thank you very much.
Thank you. Are there questions for Ian now, while the next speaker is setting up? Susan Fitzpatrick, yeah.
Yes, just a quick question. I might have missed this, but to get an RCR of 1, I know it's probably field dependent, but about how many citations are we talking about?
So in my field, in neuroscience, it's probably about 6 citations per year.
Is there any other questions?
Where did I go? Where did I?
Okay.
I was here. I'm searching out here for where I disappeared to. You put me up.
Yeah, I did.
And you put my name specially so I would find it. If anyone finds it, you can.
Let me just check it out.
It disappeared. This is from 3 minutes ago.
This gives us more time for questions regarding metrics and indicators. You might realize that many of the conferences that are currently funded by the CICIP program, they are focusing directly on metrics and indicators. And some of us which attended the Science of Science event at the Library of Congress actually got to discuss this in much more detail. I believe it's very interesting to understand that the field of scientometrics, infometrics, bibliometrics is dominated by counting and measuring and doing analytics of existing data sets. And I think this number of having numbers associated with an individual or an institution or an entire country is also very, very widely used in Europe. Those of you which don't know about the Blue Sky Conference, this is a conference which happens every 10 years. It's organized by the OECD. And it's happening this year, actually, in Ghent, in Belgium, in October. So those of you which are interested in metrics and indicator development, please feel free to Google for Blue Sky 3. It's the 3rd conference in this series. So some of my colleagues, they actually have attended all 3 of them. But if you are interested in these kind of indicator developments, this is really the place to be, because that's also bringing together all the different member countries from the OECD and other countries which are very interested to measure things correctly. So
It was mysteriously hidden by some dark cloud. And then when he put on the original version, it said, there is a version already there. It is just invisible. And we know about the invisible cloak that they have created, but I've been told by somebody who's an expert in whatever it is, photonomics, that actually you couldn't see the thing that they can cloak in any case. But this is going to be it needs a huge microscope to see, because it's very nano, the cloak. So this is going to switch to private sector things, in which what we're trying to measure is innovation. And I give you the problem. This word is used every place, and all you just have to go and say is, gee, where do we have in any statistical yearbook or wherever a measure. There is no measure at all. We have GDP, we have employment, we have a lot of things. And when you go to the indicators of innovation, you quickly see they're a mess. They mix together per capita measures with aggregate measures. So if you look at any one of the GDP, innovation indicators, you'll see China gets a #1 for science and engineering graduates because they produce more than any other country. They now get a pretty high R&D over GDP, but they get very low on things like rule of law, on various per capita things, because Sweden and Switzerland are always the top global innovators. And that means if you have one good invention or something from Sweden, it's the top of the list. And that China could be producing thousands more. So it's a very weird thing. And then I just want to point out, none of these indicators of innovation have anything real. There is not any real product that they're talking about. They're not talking about some drug that was produced or anything. So as I say, there's a lot of talk but little substance. So what can we do about this? Well, first I went back to Lord Kelvin, and he said, you better be able to measure this. Now, some of you may know that Lord Kelvin said some other things, like there could never be an airplane, that all of physics now is just dull measurement, and there are a number of others. But on this particular point, I think it's correct, because just talk about innovation. So what can we do to measure innovation in a substantive way that we actually can touch it? And there are two ways that we have at the moment. And so one is, and this is on the NSF Börner database, it's the European Community Innovation Survey, and I'm going to be giving you some data from a Chinese data set that has the same question, which is they ask a company, have you brought any new products to market last year, or last 1 to 3 years? And then finally, they ask, and how much dollars, renminbi in my Chinese data, come from those new products? So you're able to calculate a measure that is the fraction of a company's sales that they report as coming from products that they brought to market, last year. And that is the sort of more or less the official definition from Schumpeter to the Oslo Convention about innovation. So we have that question. The other way we can gather this kind of information is to web scrape from companies that announce new products. Anytime a company has a new product, it's going to publicize it. Nowadays, it'll be on the website. And if you look at an incredible website, GE just lists products after products after products that are new. And then there are other places you can get. If you go to Amazon, you can just follow, okay, what computers are being sold on Amazon? And when there's a new one, it's a new model or et cetera. The catch with the information that exists in these websites and the new product announcements, you don't know often the price, though companies will, you can track that down, and Amazon, it will give you the price, but you may not know the quantities. And then you have this other problem that maybe the new model that I just announced is that I sold, I don't know, light purple shirts, and I now do dark purple shirts. That's my innovation, and in the fashion world, that may indeed make me a lot of money and be very important, but somehow or other, we're a little uneasy that that's what we're talking about. So I'll tell you what we do to try to deal with this. I'll now give you some information from both methods. And so the first one comes, I've been working with Chinese data, and so China asks the following question of their firms. What is the output in monetary value from new product in your firm this year? And that's actually a little advantage over what the Americans and the Europeans do, because it gives a yearly amount. The Americans and the Europeans say the last 1 to 3 years, and it just smushes things over. We took a balanced panel of Chinese firms, and so here they're called stable incumbent firms, meaning that every year in the data set they existed. It's a 9-year data set. And then we just calculated the fraction of the Chinese firms we have the fraction of the firms, but then I really want to put stress not on the red line, which is the fraction of firms, but the share of output from new products. And what you see is that in the last decade, 1998 to 2008, slightly, the newest data is not available from China, there was a doubling of the fraction of new products that came reported by these firms. So there is, by this metric, a giant increase in, quote, innovation. Now, these new products could be things that were already existing in the US, Japan, or somewhere else, but to the Chinese market, these are innovations. And 20% of your sales to come from a new thing is a very large number, implying that there's just a lot of stuff going on there. We then looked at these firms and we said, well, okay, how often do they bring out a new product? And so we have this in this balanced panel, 28,303 firms. Most of them never bring out a new product. They just tell you, nope, 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 nope. But then we get 1,221 that in every year of the sample tell you they bring out a new product. And if you go over to the share of value from the new product, they bring out 57.57% of the amount of money of new products come from these firms. So you have basically serial innovators who are doing all of the bringing out the new stuff. And you have a lot of other firms that keep producing the same thing year in and year out. I don't know that this is true in the US as well, but I would put a chunk of money down that it is. It'll be true in literally every country. The innovations are driven. And these companies, they are companies that that have lots of patents, that they do lots of R&D, and they are clearly, in that sense, driving this market. The things in between, randomly assigned ... was just to make it absolutely clear that this bifurcated distribution could not possibly have been generated by a binomial distribution or any kind of a reaching into a hat and saying, well, some firm, of course, will pull out with 9 innovations, even though it's no more innovative than other people. That's clearly not the case. Then we took a look at an interesting thing, because this question struck me as a little weird. What's a startup company? A startup company comes into the market. It had nothing produced last year. In some sense, you start to say, well, 100% of my things are new. After all, I've never had any other products. But it could be I'm not really bringing out anything new, or maybe I'm producing the same thing that my competitor over there produced, and I'm just, it's new to my company, but it's absolutely not new to the market. And the Chinese data, unfortunately, don't do what the Europeans do in depth, which is ask, is it new to your company? Is it new to the country? Is it new to, et cetera? So we looked, and this very interesting year T0, the dark line is for the companies of the first year you appear in the survey, and we calculate it's also the year your firm says they got legally originated, and we do see there's a chunk of people far over there reporting, yeah, 1. They came into the market, well, of course they had to do this. Then we took it for a year later to kind of correct for that early thing. There was no other good you could be comparing yourself to. And it goes way down. But you do see this bifurcation here. Some of the startups are not reporting that a new product, meaning they're interpreting the question, let's say, as new to the market rather than new to the firm, but some of them seem to be reporting it the other way. So that's a nice little check. So we've done a whole bunch of other analyses of these new products in China, and I just summarize what we found. The innovative firms, those are the ones that are doing every year innovating. They have greater sales growth, high and increasing productivity, and they have a higher survival rate. Well, if you're in our serial innovator, you have to survive because you're in the survey every year. But you can go down to the companies that reported 8, 7, 6 years of the 9 years, and you see they survive more as well. And they have greater R&D. And it's very interesting. The Chinese divide up patents into 3 ways. There is call it a real invention patent, which they think that's the one that really the patent investigators go over carefully. There's a design pattern, and there's a utility patent. And we found that these innovative firms had more design and utility patents. And first we thought, that's strange, because we're thinking of a patent as something, the innovation one is or the invention one. Well, of course, why would you take out a design patent? Well, it's because you're about to bring a product to market, and you want to patent the design. If you have a really bigger discovery or potential, you don't know if the product's going to come out or not. So it's an interesting, different take on there. And then in the market, if I bring out an innovation, a new product, we find that it will eat up some of the sales of my competitors, it will eat up some of my old sales, and it grows the market. So there's a 3-way effect going on. And then I just said at the bottom, we need more information about these new products. And we have discovered, but have not yet convinced the Chinese statistical people who have the data, that they did a question where they actually asked you to follow through the companies. You brought out a new product 5 years ago. What are the sales of that product today? So you really could follow a life cycle, products coming in, et cetera, which I think is very valuable. Now let's go to the web scraping, the other way of doing this. My original plan was I was just going to, write a program, or have a friend of mine at Penn State actually his team was going to write the program, and they would just go to websites and they would pull down all the new products. So we'd have a big giant database. Turns out that's pretty tough. Firm websites are not built in the same way. They change from year to year, indeed, as they're trying to publicize things. And you really can't do it with a web scraping program, and you need humans. And I do have a small team of Chinese volunteers who are helping me do some of that. The second plan we had was to go to lists of innovations. The R&D magazine, for instance, has the 100 most important innovations of the year. Well, it's a little strange. You put your company's innovation up, so it's a self-declared important innovation thing. But there are some others, the Cleveland Clinic lists medical innovations. And again, there's a wide variation, and they don't tell you anything about did it sell very much or not. And so you'd have to search that. So we've now latched onto a plan of using Amazon data. I'll give you the example of Amazon China in a minute, where we do cell phones in China. And I have a postdoc, Jorn Bonke, and he is a co-author, Mendel, and they have really been doing an incredible job of getting millions of observations from Amazon on the price and the sales rank, which gives you the quantities. So here's what we did with cell phones. So our database, we have 1,536 cell phone models. A cell phone model is great because basically it does not change its quality over time, or maybe some minor things will be done. So that means once you have a cell phone with a given set of qualities, it's constant. And so what goes on as innovation occurs is the old cell phone is no longer produced. It's like the old Windows, is no longer produced or supported, and you they're going to have everybody do Windows 10. So we obtained from Amazon China and a particular website the prices for all of these cell phone models. We identified a whole bunch of attributes, and then we used the Amazon sales rank to determine the quantities being sold. There's some other stuff involved. It's a little more complicated. We estimated what they call a hedonic price regression, based on the attributes of, so here are a list of attributes: display size, display resolution, network processor core, clock speed. These are the attributes of the cell phones. So we had that for 1,700 models. And then we take what is the going price for, what was the price at the period of time, it's every year the price is. It's a thing. And then the column to look at is called share weighted. So we calculated this hedonic price where we weighted the number of sales. So we found some peculiarities in the columns 1 and 2, but basically it was because sometimes there would be a small model that didn't sell too many, which was leading to some odd coefficients. It's, these are highly correlated things. In any case, we end up with, when we do our weighting, extremely high R-square, we're doing a very nice analysis of what are the attributes. What you then do, you take these weights and they give you the quality of every cell phone. So as the cell phones get better, the quality should be going up. These are weights averaged over the whole period on the assumption that consumers their tastes are not changing. And this just goes to the interesting thing. There are 3 lines. The middle line shows the average quality. And then what's going on in this market is that new entries are the higher line. New entries always come into the market. A new model is introduced. It's got better quality than the older models. And then the bottom line are exits. Those are things no longer being produced. So what you're observing is a rising quality, but the reason the rising is going on is the new innovations come in, they're better, and they quote kill off, if I can phrase it right, the old creatures. And so it works extremely well. We haven't yet done this for the US. We're going to go to see whether the Chinese innovation market is any different than the American. I can't believe it's going to be much different, that you'll be able to discern. It's the Samsung, the same companies' models are being sold in all the countries. There's not going to be much difference. And the big Chinese models, which are rarely sold in the US, but they are really sold because they're called AT&T models. Or when you buy a phone that does not say iPhone or Samsung, it is often with an American brand on it. It's often made actually by the Chinese Xiaomi or Huawei. Okay. Okay. Last thing. Sorry. But maybe you counted my wasted time at the beginning. I don't know. And this is what my postdoc and his co-author have done. And they have now gotten, for 135,000 Amazon products, 2008 to the present, all kinds of the price and the quantity sold. And obviously, what we're trying to do now is identify the attributes of at least some of these products. We don't expect to do all 135,000 and trace them and do the same kind of analysis we've done for the cell phones. So you would be able to say, in this industry, in this product class, here are the innovations, and they're rising quality. Why? Because we know what the consumers value, and they're increasing those things. So that's our goal. And eventually, since we know the firms, we could link this genuine measure of innovations to the firms that are producing the innovations. And that's the end.
Thank you. Are there any quick clarification questions while the next speaker is setting up?
This is Arash from Virginia Tech. I have a question. In first part of your study where you studied startups, have you been able to look at differences in industries, or did you find any differences in the different industries as far as the share of innovation in their products?
Yes, we can. No, we haven't. We were just happy that we got a general result at the beginning. This is very new research, and we're getting, I was in China last week, and the Chinese were telling me, you know, the new products, to be declared a new product, it's not really the company who tells you. The city government has to approve. So there's actually a quality control on the new product. I can't just announce I'm pulling a new product. So we're actually in a refinement stage for the moment of making sure, you know, but yes, we can do that. So we have 20,000 firms or so, and we can do quite a bit.
Thanks.
Yeah.
Okay, I feel like a little outlier here. I'll talk about analysis from industry point of view. So this is life in the industry, and I'm calling it operational big data models. Those are the two distinct features. One of them is big data. I come from PayPal. I lead their data science team, and we are using PayPal data and other data in order to analyze at a very granular level, customers, which are both merchant and consumers, but our models need to be operational. That is, when we build a model, the model output needs to be used in the field, and in a short period of time, the output is measured. So this is where the operational come from. And this is kind of different that whether it ends in a publication or ends in the hand of business person who actually have to generate some monetary value out of the results. And I will talk about three aspects of this. One aspect is the full spectrum, which we expect a data scientist to work on the complete spectrum. On the left, you would see that we have observational big data. Big data is messy, whether it's from corporate or whether you take it from the outside. It's messy, it's unreliable, it's scattered, it's not complete. But you have to make sense, and a previous speaker talked about linking. You have to have that to tie all the pieces of data together, and this is part of the art of what's known as data science. It's not called data arts and sciences, but just data science. A lot of art, how you actually link and bring it, and the major task that take a lot of very hard work, and some speakers alluded to it, is in the middle, is called data munging. You cleanse the data because when you need it, bring it to an algorithm that does the model. The algorithm usually like to get very neatly organized data. That is, consider Excel spreadsheet with all the fields are in with very few missing values. So you have to take from messy to very well organized, and you do it by all kind of jargon things called feature engineering. You just build a data set that you can use the model on. And it's now became a common wisdom, which is true, that this particular task in the square, in that frame, takes about 80% of the time of your work. So this is a given. So everybody who wants to get corporate data need to know that it's not something that is nicely waiting for you, but it's scattered all over the place. There is a lot of work to understand where the data, and I didn't even touch the point of what the heck the data means from business point of view. You see a number, you see a name, what does it mean? How can you put it in a computation to get a result that is meaningful? Following that, what you do is you build a model, and I talk very briefly about this, but I would like also to stress the other part, which is the validation. Who is the consumer of this, the output of these models, and how the consumer should evaluate and say, yes, I trust it, I want to use it. This is a major part of the work in this particular one. So let's talk very briefly about the infrastructure. The infrastructure that is being used, increasingly used by corporations right now, especially where I come from, which is the San Francisco Bay Area, the Silicon Valley, is used a lot of open source platform, open source tools, and just the names here, Hadoop, and Hadoop, which is, of course, the big data lake. A lot of databases are being now transformed to open source, to Hadoop. Spark is the new shiny object of very large-scale analysis at high speed. H2O is known as the machine learning platform to run very large-scale machine learning model on a cluster of machines to make it work fast. You can do big servers or many small servers, up to you. And the thing is, the data goes there. You have to collect, you stream it, so it's not static data. You get it there day in, hour in, and if you're lucky, moment in, even second in, any time. You want to take real-time action, might as well take the data shortly, sometimes during the transaction that happens. So you need the data fast. The cloud interface, you can have all kind of variation of this, and the training data, the data that you use the model to train, to build the model, is very large, in the millions or tens of millions of rows of cases, and large number, up to thousands or even sometimes tens of thousands of columns of features of that of the particular model. And the idea there that we try to do is not to aggregate, but to have answer per particular object. Object is, in our case, is a customer. What is that impact on a particular customer? So you have to tie a customer, mind you, not name, but encrypted ID, with what you want the results to be. And then there is something that I stress, because collaboration is not just in data. Collaboration is also for the work of the analyst. And there are quite a few tools where you can share your models. You can publish reproducible modeling. For example, if you use R, you can use the package Sweave, and then you publish both your model and your article and the data, so you let others repeat what you've done. And similar thing in Python, you can publish what's known as notebooks with the data, with the code and everything. And I'm not touching about whether people want to share their code or not. I assume it is given. But if you want to share, you want to know what model other people did, etc., if this is encouraged by the company, this is very, very useful. And also, for those who run big data sets, it's very useful to have a common collection of the queries. So when someone gets into the data, they don't have to guess, to start from scratch, to write the new query to get the data. In order to get these results, here some other people do those queries before, so you learn from other people's experience. So it's basically a meeting place, a sharing place, collaboration for the analyst. It's very important if you're looking not for a particular analyst, but a group of analysts, you want to increase their productivity. Let me touch a little bit about the modeling. The modeling that are done, basically that are done in the industry a lot, is basically built on machine learning, where the results is the accuracy. You want to know the results, less than the inference or sometimes you want the variation around the results, but what counts is the accuracy of the results. So at the top level, a machine learning model is a complex computational algorithm that runs a lot of calculation. At the end of the day, a lot of them will give you a set of numbers known as scores, one per every object. So if you want to analyze millions of customers, every customer will get a score. What's being done in the score is in the context of the analysis. And there are all kinds of algorithms, all of those that you hear, they're doing similar things, except for the clustering, of course. Tree-based ensembles, you have the neural net, you have the new shiny object known as deep learning. They're all doing similar things in terms of giving you a score that tells you what is the probability that some outcome will be. The more accurate those are, the better it is, of course. But a very important part, okay, you build a model. Now, how good is the model? If you run linear regression, you have the R-square. A lot of them are done on classification. Basically, you want to have categorical output, and you want to say the score means what is the probability that this particular case will go to value 1 or value 0 or value n of the categorical output. And those you can do how many false positive you have, how many false negative you have, and you have to remember that they have different costs. And you have to do this, so it's not, false positive is not the same as false negative. For example, I'm saying jokingly that for PayPal as a payment company, false positive, they do the risk. False positive costs us money. False negative costs us money. We didn't identify. False positive will cost us PR because people go on the web and say, look how PayPal blocked my account, etc. Which one of them is more important depends on what you and how you consider it in the business. But it's not like in communication, either 1 or 0, 0 instead of 1. They have different, and you have to do it pre-production because it has to go to production to make sure that it holds water. And also, there is, when you have all of these features, you have to argue which one of them is correlated and which one of them is causation. And a lot of time you go into A/B testing to prove causation. And then you want to gain a trust in your model. Because remember, you give the model, you are as an analyst, you give the model, you don't publish it, but you give it to, sometimes you give it to a computer to start running actions based on it. Sometimes you give it to business people who take action on it. And taking the action costs money. For example, you have to set the system so that it actually basically start working based on the recommendation of the model. The model is basically a recommendation. So when you get those scores, the question is, what is the treatment? What would the business do with the results of the model? Which is non-trivial. And by the way, a lot of those models have to do prediction, and the prediction is the evolution of the customer. So you give the customer history and the state of now, and then you will say with the customer churn, maybe you want to give them incentive, or will the customer grow and become a very successful customer in which you have to give them a very good treatment to help them work better with your application, with your products. And so, and the score, basically, when you give the model and you talk with the consumer of the model, you have to, the model results, okay, let me take it just one thing back. You have to look at the model, you have to convince someone that this is the right model for them. and they would ask you, why should I believe you? And here you come to a very interesting trade-off in modeling between interpretability and accuracy. The model we saw in the talk before is interpretable. You have regression in every one of the features, you have a coefficient, people can understand that. If you take a model, one of the machine learning ensembles, as in random forest, as in boosting algorithm, this is a black box. It gives you the score, and at best, it will give you the least, it will assess the importance, the impact of each and every one of the variables on the whole model. But if you say, okay, on this particular, what is the impact, what is the factor that affects this particular, then you have to go and do something else. And so the idea is at what level you need to articulate, to rationalize the score for any particular customer. And then when you go to adopt you have to identify champion, someone who has the business, believes in the model, and will take it and basically act upon it. And the incentivize adoption of the model. Why should they adopt the model? You have to show that this is going to be significant impact. Because as the cliche goes, there is statistically significance and there is business significance. And so you want to show that their business will be significantly impacted by the results of the model, given that the model is correct. Another thing is you want to avoid impression of positional bias. Some of the models that were done, there is a very famous case of the Boston street potholes that basically they did it by crowdsourcing, basically, and they discovered that basically that they fixed potholes of neighborhoods where people are using, have the internet and everything, the most affluent ones. So the model did what it is, but it has a positional impact because the sampling was biased toward more affluent neighborhoods. And so another thing is, can you integrate when you have a very big project, can you start small and integrate it and build trust gradually? This is really important because you reduce the risk of adopting it. And then these models are, I am trained engineer, so it took me sometimes, I realized I'm in social science now, and the model, the underlying environment changes all the time. So it's not one model that will keep it, you'll keep it forever, but you have to go take new data, train new model, create new results, and train. So this is a cycle that goes on and on. You correct inaccuracies, and you build model based on the improved, the more recent data, because sometimes data 5 years ago is no longer relevant today. And another thing, and it's extremely important, and this is while the model, you succeeded, and the model is now in production, measure the results. You have to come up and say, based on this model, here are the benefits that came out of it, which is not very simple. How can you identify? Now you have model your own action, basically is in how you actually do causation. How can you identify the impact of your particular model? And finally, since this is innovation, how do you predict innovation? And I would say, think out of the box. If you predict innovation, you want beyond just measuring past innovation, you want to predict who is going to innovate in the future in order to put your effort in it. So if I am predicting which merchant will grow and will be successful in order to put revenue, this is the same family of question to ask. And I will stop here. And thank you. And if there are any questions.
Thank you very much. Are there any clarification questions?
Ben Schneiderman, University of Maryland. I have to speak up for the idea of visual analytics. You didn't include visualization as part, unless I missed it, as part of the ensemble of ways of verifying the data and the model, cleaning up errors, etc.
I fully agree with what you said, but I think I was given like 10 minutes. I had to do selective. In the full version of it, visualization is one of the most important things.
I would say it's an essential
Yes.
component in making safe data mining. The number of cases I have dealt with where data mining results were completely useless because the users had no idea the data was so flawed. And I think without doing that, you're risking dangerous mistakes and mistaken results. Blind data mining is dangerous. Thank you.
Absolutely. Even not lying, I won't accuse everybody of lying, even doing things without knowing what basically you're doing, not knowing the data, is also dangerous. But when you do production type actionable models, it will come back to hit you in the face after that. That's if it is not there. It won't even be both on that, and there are some, and visualization is extremely important. And I know for the organizer of the conferences, but I thought I would talk about this. And given R and Python, it's come with visualization. Without it, they are basically the tools to do that. And looking at the data and understanding the data, part of the new tools, as in H2O, you may want to look at it. It's a very interesting. You can run it. Open source, of course, free, you can run it on your laptop or on a big cluster. It gives you also the ability to build very complex models with graphical user interface, not writing a single line of code. And we'll give you the chart and all the chart and examine all the variables, etc. And my opinion on this, it's good news and bad news. It's good news that people who don't know anything about statistics or modeling can build very complex model. And the bad news is that people who don't know anything about statistics and modeling can build very complex models. Yes. So thank you for your comment. I agree with you.
If I can continue, since there are no other questions, just the number of cases of a model I've seen of predicting consumer purchasing behavior came along and there was no data for April and the analysts had no idea and the models therefore missed all the spring sales. Other times just repeatedly error data, duplicate data, and these are not visible and not apparent because the model has failed in other ways. And I think understanding bimodal distributions, errors, anomalies in the data are prevalent, and they're just every project, and I just think the cure is good visual analytics of looking at your data.
Yes, and another idea is outliers and null values, and a lot of things. This is all falls into this data munging. You have to make sure that the data is there, and you know that the data represents, and you can rely on it.
Wonderful. Thank you so much. Last but not least, we have Grace Peng, also from NIH, and she is presenting on challenges on how to model and model share, and also how to describe models ultimately.
Thank you, Katy. Good morning. And I am a program director at the National Institutes of Health. And yesterday you heard a lot from program directors in their funding opportunities for the community. And so what I'm going to talk about are what are the challenges that we go through when we're developing those funding opportunities, and also after we've funded the projects, how we deal with the challenges of data algorithms and infrastructures for sharing and analyzing and understanding the outcomes of what we've received through these results. So I'm more presenting challenges rather than solutions. So the previous talk was very helpful in helping me discern some of these things. So I also wear a hat where I chair the Interagency Modeling and Analysis Group. This is a group of program directors from government agencies across the federal government, including NIH, NSF, FDA, Department of Energy, NASA, the Department of Agriculture, Department of multiple components in the Department of Defense, the Veterans Affairs, and also the Intelligence Agency. And so we're all interested in promoting modeling and analysis of biomedical, biological, and behavioral systems. We have over 80 program officers in this group, and we get together on a monthly basis pretty much since 2003, because we actually find that it's very useful to leverage each other's programs in trying to promote this field. And so since 2003, we've been promoting multi-scale modeling in biomedical, biological, and behavioral systems. We recognized at that point that it was a nascent field in which these modelers needed to model above and below the scale of interest and address the whole physiome, from atoms to molecules to cells to organs to tissues, all the way up to the full body. And by 2007, we were interested in going towards the population level. And so that was the challenge that we were addressing at the time of forming our interagency group. And in forming this group, we ended up creating multiple initiatives for multi-scale modeling. And through these initiatives, we funded awardees, and they are part of the Multi-Scale Modeling Consortium. We call it the MSM Consortium. And really, the synergy between IMAG and the MSM is greater than the sum of its parts, and I'm going to describe some of this right now. So in a sense, part of the infrastructure is this interaction between government funders and the extramural community. And so this is an example list of our working groups for the consortium in 2016, and you'll see there's a lot of discussions on different types of models, from systems biology, biomechanics, to some of the tools for model and data sharing, computational neuroscience, and I'll talk about a few of these groups now. So since the inception of the Multi-Scale Modeling Consortium, this group has really focused on discussions on model and data sharing. It was one of the biggest interests to promote model and data sharing, and that's why the consortium was formed. And so the discussion was, we're looking at all of these scales, and it's inevitable that we need to use quantitative modeling to understand all of these scales, to better understand the system beyond mental models. And so Ray Winslow, in this review article, nicely presented the different types of mathematical models that could be used across the different scales, and how the instrumentation that we have now are able to measure the data for these models and for these scales. And so the question in the consortium is, how do we organize all this in the form of multi-scale models? And so we devised a predictive model index where we would organize our models from the consortium awardees. And just picking on one of them, the open knee model. In fact, the author of this open knee model is sitting in the room, Dr. Ahmet Erdemir. And so if you open up one of these predictive model index, you'll see that the consortium devised up these criteria for the authors to populate. So they talked about, they wanted each modeler to describe what is being modeled, for example, tissue, organ, biomaterial, briefly describe the description and purpose, describe the spatial scales, the temporal scales, and what is the status of the model? Is it under development? Is it in the pipeline, or is it being validated? Is it being used in a clinical setting or a non-clinical setting? And how has it been validated? And so that was a big question, was validation, and then providing links to the project and the investigator, as well as keywords to find this. And so this is the template that we came up for the predictive model index. It was nice, and as you saw, we had some people populate this. Ultimately, we need to figure out a more dynamic index in which these index criteria can be updated on a regular basis. And so that's how we ended up articulating the models we have in the consortium. And so the discussions continued on model sharing, model data sharing, developing standards, and ultimately the discussion came to the point where we really need to start with model reproducibility. We cannot share unless the model actually works and that somebody else outside of the lab can actually reproduce the same results of the model. And so the discussion was, well, we're all in agreement with having this come to play, but how do we do it? And the conclusion was we've reached a brick wall. The only conclusion is we need incentives, and the incentives of the academic community is publications. And so one thing that I did back in 2013 was using my role as the IMAG chair and also coordinating the consortium of investigators. I joined the IEEE EMBS committee, the Engineering and Medicine and Biology Society Technical Committee for Computational Biology and the Physiome. And so I felt that this was a way to sort of interface government, academia, as well as societies, in which the IEEE has already a whole group of publications, and they have publication committees to interact with the editors-in-chiefs of these publications and to talk to them about model reproducibility and how we can possibly change the culture of publications to require the modelers to publish their models such that the reviewers will have access to the models to be able to reproduce the models as they're reviewing, such that the readers can click on a link from the paper and reproduce the model. And so this committee was formed. We recruited over 15 editors-in-chiefs from different journals that focused on modeling. And so these editors-in-chiefs all agreed that this is a great idea. And so we started having discussions in the different communities. We met with the systems biology folks, we met with the biomechanics community, and we decided those two communities are a great start because they're very on different ends of the modeling spectrum. They're very different communities. And we discovered that each of these communities have their own culture of modeling and the types of platforms they're using, and how one community might be using, the systems biology community, for example, uses more of the open source type models, and the biomechanics community uses more of the commercial type products. And so how do we get together to figure out, is there one unified response that these publishers, these editors-in-chief can give to the academic community to really produce reproducible models? And so what is going on right now is, in this technical committee, is the production of a special issue on model sharing and reproducibility. And so it's going to be in the Journal of the IEEE Transactions on Biomedical Engineering. The goal is to raise awareness of the importance of model sharing and reproducibility while understanding the differences and overlaps between communities. And the format of the special issue really is a collection of reviews, perspective articles, and research studies related to reproducibility of computational models in biomedical research. So the hope is that in this special issue, we'll have actually almost a trial run of a model creator and a model user going through their experiences on how they developed the model to make it reproducible and how a user used the model either successfully or failed. And the special issue itself is an experiment on reproducibility, in which we're hoping that the models that are published will be reproducible in the public. So it's an interesting special issue that we're trying to have occur. Again, it's for systems biology and biomechanics. The co-editors, actually Ahmet Erdemir in the room is one of the co-editors along with Herbert Sarro. So that's another experiment in how we want to promote model reproducibility. So going back to the working groups, there's also a committee on credible practice of modeling and simulation in healthcare. And this particular committee is jointly organized by IMAG and the MSM, and actually Ahmed is one of the co-chairs of this committee, and he told me to let you all know that he's open to receiving new members on this committee. And so this committee was really helpful in the last couple of years in developing a survey to survey 10 simple rules for credible practice for modeling. And the idea is first to form guidelines on what people think are the 10 simple rules for credible models. And so IMAG built on this, and in our current funding opportunity for multi-scale modeling, we are actually requiring a model credibility plan based on what this committee has found over the last couple of years. And so if you open up this funding opportunity, which is PAR 15085, which is for multi-scale modeling, you'll find this requirement. And for the model credibility plan, we're asking the investigators to delineate the strategies and metrics they're using for evaluating the credibility of their proposed multi-scale model, and what kinds of questions they're addressing, which questions of interest within the intended domain of the application in biomedical, biological, behavioral, environmental, clinical research. So they are to propose a third-party evaluation, someone outside of their lab, to use these metrics. And the intention is to use this model credibility plan as a first step towards model sharing and reuse. If you cannot convince one third-party person to use your model, you really have no need to share it. And this was what the previous speaker also said too, to find a champion for your model. So when I talk to both the applicants and the reviewers, I close the loop and tell them both the same things. And I tell the applicants, you know, you really should take advantage of this and allocate funds to really allow the third party to evaluate the credibility of the model within the intended domain, and to allow IMAG to help you discern this third party to evaluate the model within the funding period. So this is really an activity that the applicant should take advantage of, in fact, to allocate funds for. So this is another solution that we came up with in order to promote the first step for model sharing. So there are still current programmatic challenges. I'm involved in several initiatives, and questions are, how do we share and integrate complex multimodal, high throughput, and sparse data from a system that we're collecting? And how much do we really push for developing standards, and when should we do that? So I'm just going to give you two really quick examples that which you might have heard of. So one of the new programs at the NIH is called Stimulating Peripheral Activity to Relieve Conditions. The short name is SPARC. It's a new Common Fund program at the NIH. Common Fund just means it's a trans-NIH program with multiple institutes participating in it. And basically, the issue is you probably have, you know about the pacemakers and different neuromodulation stimulation devices for deep brain stimulation. There are also ones for the heart, for the kidney, for the pancreas, the stomach. There's lots of neuromodulation devices out there to treat diabetes and inflammation. The issue is that some of them work, some of them don't, and the reasons are we really don't understand the mechanisms of action. And honestly, what happens is they find a nerve or some area, a surgeon realizes that if you stimulate or inhibit or you cut the nerve, something happens. You know, they actually just approved a device for treating obesity. And the results are not so conclusive that it will work all the time. And the reason is, again, they're just sort of doing input-output, stimulating and observing, and not really understanding the pathways within the human body. So this is the visceral system of the human body, which is below the neck down, and these are all the organs. And the idea is SPARC is promoting the study of understanding these peripheral nervous system's pathways, to map these pathways, to understand how the kidneys connected to the heart, to the urinary tract, and all these systems and how they interact and map together to control our end organ functions. So there, you can imagine there's a lot of data to be collected. And we've broken up this initiative into 4 different parts, where there's a part where they're collecting anatomical and functional mapping data from the major organs. We're also developing new technologies for this mapping. And then we're also using existing approved marketed devices for other conditions. to further discern whether or not we can provide a next generation neuromodulation device that's much more informed by the mechanisms. And so this gray box is really what we're focused on for this meeting here, is this data coordination box, in which it's designed to organize all these efforts together in form of a data coordination mapping modeling committee, or center, I should say. And honestly, we don't really know how that infrastructure will look like. It's a very complex problem because we're talking about many forms of data, many forms of technologies, legacy data, new data, and how do we develop an infrastructure that will have models that can predict, for example, if you stimulate here on the vagus, how will the kidney react? Or if you stimulate here on the spinal cord, how can you control bowel bladder function? And those things are what we're trying to get at with this data coordination modeling mapping center. And this is one of our biggest challenges. Now, flipping to our second example, looking up above the neck, you probably heard of the President's BRAIN Initiative. It's brain research through advancing innovative neurotechnologies. You can find it by searching NIH Brain. And I'm just going to go through the 2025 goals. There is a huge process in delineating the goals of this initiative. And so the goals are supposedly to go all the way to the year 2025. And the idea is we want to discover diversity, understand the different brain cell types. To this day, we still do not know all the cell types in our brain. And to map the brain at multiple scales, generating circuit diagrams, much in the sense of what I just told you about Spark in the peripheral nervous system. This is circuit diagrams in the central nervous system in the brain, from synapses to the whole brain. And then forming a dynamic picture of the functioning brain by developing methods of high throughput recording and stimulation of neuroactivity, so lots of electrode development, technology development, and linking the causality of brain activity to behavior. So how do you connect brain behavior, like understanding cognition and perception and memory, to different neurons firing in the brain? And then, so this is brain cell types, tool for circuit developments, technologies for monitoring neural activity, and precise interventional tools for linking causality. The next goals are identifying fundamental principles for conceptual foundations, using the procedures that humans go through now in regular clinical practice to understand the brain, and also to integrate new technological approaches. So bringing together the latest generation of imaging, calcium imaging, electrophysiology, quantitative methods, models, and then having all that come together to understand cognition, emotion, perception, action, and health and disease. So theories, human neuroscience, and integrative approaches. Now this number 7 ultimately is what we want to achieve from the BRAIN Initiative, right? To understand how the brain works. And again, we're reaching the same conundrum with Spark as we are with BRAIN. And where do we go with all this data? How do we actually bring all this data together to have groups communicate with each other to understand memory or cognition? How do we actually share and integrate this data? And so this meeting has been very helpful in helping me discern, but I just wanted to let you know that these are some of the things, it's just examples, and there are other initiatives at NIH that are also collecting lots of data, and we're all having the same issues of how do we analyze, interpret, understand the data. And so modeling, of course, is something that I'm trying to promote, and I am very open to other ideas as well. I just wanted to use the last few slides to advertise our Multi-Scale Modeling Consortium meeting is having our face-to-face meeting at the end of October. It is an open meeting, no registration. You're welcome to attend. It's at the NIH back here in DC, so you're welcome to come. If you go to the IMAG Wiki, just search IMAG Wiki, and you'll find information about it. And thank you very much.
Thank you very much. I got a question, Grace. So as you know, many of us here in the room are modeling science, technology, innovation, not necessarily the brain or other organ systems. Would you be open and interested in actually receiving submissions to the special issue, but potentially also to the funding opportunities that look at the structure and evolution of biomedical research over time using computational models? Because I think that's a question that many of you might have.
Well, in most of the initiatives, I think we are promoting diverse teams, multidisciplinary, interdisciplinary teams, bringing in even the end users. And so I think having some of these experts on these teams to get a close-up look at what these scientists are looking at and trying to understand things would be really helpful, I think. And I think a lot of the tools and techniques that you all have talked about in this meeting could be applied and help us to think out of the box, as a previous speaker mentioned, to really think beyond how neuroscience is done now, to think about how these data should be collected and how models should be designed to drive the collection of data. So I would welcome anyone in this room to participate. I actually had a long discussion with the NSF folks, and they said also similarly in their realms they have resources which NIH investigators might find useful that might not be aware of.
Five panelists. We actually had very little time for kind of closing discussion, and I apologize for this. But we do have a break now. And so after we took a group photo of all the panelists here, please do feel free to ask all of your questions, every single one, to every single one of the panelists. And I would like to thank all of you one more time.